Okay. So what are the operations we can apply to matrices? We have addition, subtraction. Okay, so we write A plus B or A minus B, and they must have the same dimension. A plus B is the same as B plus A, and A plus B or A minus B transpose is the same as if you were to um, transpose each of them and then add or subtract them. Here are a couple of examples. So you have a 3 by 2 matrix and you want to add these two matrices. It means that you add the elements one by one. So -2 plus 3 becomes 1. 5 plus -2 gives you 3. 3 plus 4 gives you 7. 1 plus 5 gives you 6, etc. You can also do the same thing with regard to vectors, which are um, one, which are essentially also, you can think of them as matrices with a single column. So you have one column here and one column here, and then you add the elements element-wise. You can do the same thing with rows and subtract. So 3 minus 5, -2. 9 minus 4 gives you 13, and so on. If two matrices are identical, their difference is a zero matrix. So these two are identical, and if you subtract them, you get the zero matrix. The next important operation involving matrices is multiplication. And in order for the product of two matrices, the product of A, B, to be defined, the number of columns in A, the number of columns in A, what are they? N is the number of rows, M is the number of columns. The number of columns in A must be the same as the number of rows in B. So if A is N by M, B must be M by P. And then A times B, which is a matrix, will be N by P. How so? So if A and B is C, then the ith row and the jth column of this matrix C is the summation of the multiplication of the elements in A and B. And the summation is defined in this form. So you take the ith row of A, I, K. K will be from 1 to 2 to 3 to 4 to as many columns we have. So you have AI1 times B1J plus AI2 times B 2j, and so on and so forth. And that will be the ijth element of C. So in other words, Cij is the sum of products of the ith row of A and the jth column of B. So let's look at an example. So here we have a matrix A. It's 4 by 3, and B is 3 by 2. So these two matrices are conformable. So we can multiply them. And let's say we want to multiply them and we want to find the first element. Okay, so C is AB. It means that we take this row, the first row of A, and multiply it by the first column. So 2 is multiplied by 1, plus 1 is multiplied by 2, plus 3 is multiplied by 3. So first row multiplied by the first column. This is also known as an inner product of two vectors. You have a row vector, you have a column vector. Then imagine you want to know what's the element C12. C12 means first row, second column. In order to find the entry in the first row, second column, we take the first row of A and inner product it with the second column of B. So we take this and then we multiply it by this. So you have 2 times 4 plus 1 times 6 plus 3 times 8, which you have here. Sorry, here. Okay, you got the idea. It's here. Now, if we want to find the entries of the second row of C, we go to the second row of A and inner product them with the first column of B and second column of B. So we have 4, 1, 6, 2, 5, 3. Multiply sum. Then you have 4, 4, 6, 6, 5, 8. Multiply. And then you do this, and you end up with this matrix. So C, which is the multiplication of A and B, is recall A is a 4 by 3 matrix, and B is 3 by 2. So AB will be 4 by 2. 4 rows, 2 columns. Note that if A times B is defined, it does not mean that B times A is defined. If A and B are square, then both are defined. Here's an example. And in general, AB is not the same as BA. So here we have two square matrices. So the number of rows and columns is equal, and for the two matrices is also equal. So both A and B, AB and BA are defined. But what is AB? AB is 1 times 1 plus 3 times 3, which will give you a 10 here. And you have 1 times negative 2 plus 3 times 5 gives you 13, and you just do the math and you fill the rest of the elements. Now if you do B times A, you get a different matrix. So AB is not the same as BA. There are cases that they are equal, but in general they are not. That was multiplication. Now there are some general rules that we can use for multiplication. That's A times the sum of B and C is the same as A times B plus A times C. And A times the multiplication of B and C is the same as AB times C. If you have a multiplication of two matrices, and you're looking at the transpose, what happens is that the order of the multiplication will be reversed. So the transpose of a product is the product of the transposes in reverse order. A transpose A is a scalar. A transpose is a matrix, so we call this an inner product and we call this an outer product. A transpose A is a row vector, AA is a column vector, and A transpose A is a scalar. We call it a quadratic form because we have A here and we have another A here. Let's look at it. Let's look at some examples. So I suggest that you write these on a piece of paper if this is very new to you. So you have A is a 2 by 3 matrix, capital A. Lowercase a is a column vector. Lowercase b is a column vector, and lowercase c is also a column vector, but c is two-dimensional, a and b are three-dimensional. Okay. So A is a matrix, B is a vector. So AB is also a vector. You have a 2 by 3-dimensional matrix, and you have a 3-dimensional vector. So AB, you have the inner product of this row vector with this column vector. So you have 2 times 3 minus 2 times 3 plus 4 times 4 gives you 16, first element. For the second element, you have 1 times 2 plus 3 times 3 plus 5 times 4 gives you 31. So AB, even though B is a, so you see here, what is A doing? A is a matrix, and sometimes we call matrices in linear algebra, they're also known as, they perform linear transformation. So we are transforming A is transforming this three-dimensional vector 2, 3, 4 to this two-dimensional vector 16 and 31. That's also another way of looking at it. So we're going from a three-dimensional space to a two-dimensional space. So, and dimensionality reduction is a big theme in data analysis. And what does the dimensionality reduction, what's the objective of dimensionality reduction? It's to reduce the dimensionality. Obviously, we have a lot of data, we have a lot of variables, and we believe that there is some sort of structure that can be represented in a lower dimensional space. But we do not know what that structure is, and we're trying to find it. And when you find it, then you're essentially doing some transformation. You're bringing these points from a high dimensional space to a lower dimensional space, and that lower dimensional space is relevant because it, even though it's lower dimensional, it still captures the structure. So if this doesn't make any sense, that's normal. If it makes a little bit sense, that's also normal, because you may have seen it in when you were learning PCA, for example. Okay, and if you haven't, that's okay. We'll talk about it. So during the course, I will refer to different topics that may not be clear at that moment, but I like to foreshadow the concepts before going into them deeply. Okay. Now here we have another vector. Like recall, C was a column vector, so C transpose becomes a row vector. Okay, so if C is a column vector, C transpose is a row vector. So you have this row vector multiplied again by A, so now we have 2 times 3 minus 5 times 1, and that gives us 1. You have 2 times negative 2 plus negative 5 times 3, so you have 15, negative 15, and negative 4 gives you 19, and you get negative 17. Okay, so here again there's a transformation going on. You have a two-dimensional row vector. It's transformed into a three-dimensional row vector. Okay, now what about C transpose AB? This sounds a little bit more complicated, right? Because now we have 3 terms, and then the question is, where do you start? It doesn't matter. We can start with AB and then go to C transpose, or we can start with C transpose A and then go to B. Okay, so let's start with AB. AB we already did is 16 and 13, 31, right? So we end up with these 2 terms gives us 16 and 31, and then the inner product is 2 times 16 times negative 5 and 31, so we get negative 123. And this is a scalar. It's scalar, okay? Now, what about A transpose B? Well, A was this column vector, 1, negative, 2, 3. So you have 1, negative, 2, 3. And then you have B, which is 2, 3, 4. And you do the inner product, and then you get 1, 2, negative 2 and 3, 3 times 4, and you get 8. So 1 times 2 gives you 2, negative 2 times 3, negative 6, negative 6 and 2 gives you negative 6 and 2 um, gives you negative 4, and then you have 3 times 4, 12, 12 minus 4 gives you 8. So you get a scalar. And B transpose A. So A transpose B is the same as B transpose A when we are talking about, it's always the case, right? Remember, AB transpose is B transpose A transpose. So if AB is a scalar is just a number. And a number, the transpose of it is itself. So if A is a column vector, if A is a row vector and B is a column vector, then A transpose B can be a scalar. And the transpose of a scalar is itself. So, and here is an illustration of the fact that A transpose B is the same as B transpose A when A and B are both vectors with the same dimension, obviously. Okay. 2 times 1 plus 3 times negative 2 plus 4 times 3 is 8. Now, do you remember when we said A transpose is a matrix, is an outer product? We can also have AB transpose, and that will also be an outer product. And that's what we will see next. Okay. So when it comes to the outer product, here we have a column vector A and we have a column vector B, but then we have A, B transpose. So B transpose becomes a row vector. This is the form we have. Then it becomes, this turns into a matrix. We have 1 times 2 goes here, 1 times 3 goes here, 1 times 4 goes here, negative 2 times 2 goes here, negative 2 times 3 goes here, negative 2 times 4 goes here, 3 times 2, 6, and so on and so forth. So you get a matrix. Okay. So the inner product of two vectors is a scalar. The outer product of two vectors is a matrix. This is important. Just these might be very simple for you, or you might be new to it. Either way, you need to understand these concepts. And if you understand them once, then you're fine for the rest of your life, and you won't worry whenever you see a matrix vector notation, and you will realize that your life will become much easier in the long run. In the short run, you may or may not think that why I'm studying this, but in the long run, trust me, it will make life for you much easier, give you more confidence dealing with large amounts of data, and also learning new tools, because all the new tools that will be developed also in the future will be based on matrix algebra. So if you learn the basics now, then you also open yourself to learning new techniques, tools that will be developed in the future, as opposed to only knowing what you learn now. Okay, enough lecturing. Let's get back to the real stuff. Okay, now here is another example of an outer product. A and C transpose. Recall, C was a two-dimensional column vector, and A is a three-dimensional column vector. So what we get here, so A is essentially 3 by 1, is a 3 by 1 vector, right? A is 3 by 1. C transpose is 1 by 2. So the result will be 3 by 2. 1, 2, 1, negative 5, negative 2, 2, negative 2, negative 5 gives you 10, and so on and so forth. Does that make sense? Good. Okay, so we covered all of these, um, and I hope you're now comfortable with all of these operations. Okay, now before moving forward, I just wanted to go over some other things in general. So in general, if we have a vector A, we call it A1, A2 to AN, and B1 to BP, okay? Um, and this is B transpose, so it's a row vector. But imagine A and B um, are both n by 1. So you have n rows, 1 column. Then A transpose B is just first elements multiplied plus second elements multiplied, blah, 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 plus nth elements multiplied. So it's the sum of the products, so it's a scalar. Now, if you have two vectors which don't have the same dimension and you're looking at the outer product, then this is the general form you have. You have A1 to AN, B1 to BP, and then you have A1, B1, A1, B2, A1, BP. So it actually makes sense. A2, B1 is the second row, first column. A2, B2, second row, second column. A2, BP is second row, pth column. Okay? But this is what this will lead to a matrix, and that's an outer product. Okay. Now, on top of that, um, something that has a special meaning here is A transpose A. A transpose A will give you A1 square plus A2 square plus AN square, and it has a physical meaning. But before we go into that, let's look at the outer product of A with itself. And it gives us this very nice matrix which has this intuitive form, A1 square, A1, A2 to A1, AN. A2, A1, A2 square, A2, AN. So that, again, second row and column, nth row and column, nth row, second column. See? Okay. Now let's go back to the physical meaning of A transpose A. It's the length is the square of the length of a vector. Length of A is a vector, A is a point. As I said before, what did I say before about vectors? A vector, geometrically, a vector with p elements identifies a point in a p-dimensional space. And when we talk about the length of a vector, it means that how far, what is the physical distance of that point from the origin? That's the length. And the length is nothing but the square root of A transpose A. It's the square root of the sum of squares. That's it. And that's the physical and geometrical meaning of the square root of A transpose A. Now let's look at this special vector, a vector of ones, which we denote by j, lowercase j. It's all ones. And then imagine you have this square matrix of ones is denoted by capital J. Okay. Now, why do I refer to them? Because here we can do some things with it, which would be fun. Okay. So J transpose J is just the square of the elements. The elements of J are 1, so 1 square is 1, and there are n elements, so you get n. And then if you take the square root, it's the square root of n. So the length of J is square root of n. Now the outer product, if you do the math, you get the matrix full of ones, the capital J. So that's just, I wanted to also show you another example of an inner product and an outer product. Now, what else can we do with this vector J? A transpose J is the same as J transpose A, which leads to the sum of the elements of A. So for example, if we wanted to find the mean of the elements of A, so A transpose J divided by n would be the mean of A. Now J transpose A will give you a vector, a row vector, where each entry is the column sum of the entries of A. Column sum, or sorry, maybe row sum is better. I mean, what is this? This is the sum of all the, it's a column sum. This is the sum of all the elements in the first column of A. This is the sum of all the elements in the second column of A. And this is the sum of all the elements in the pth column of A. You see? So J transpose A gives us a row vector where the entries are the sums of the elements of A within each column. And on the other hand, A times J is the opposite. Now we have the sum along the row. First row, all the columns. So we are adding all the elements in the first row, all the elements in the second row, all the elements in the nth row. That's AJ. And this other thing I wanted to emphasize is this. A transpose B is a scalar, so it's equal to its transpose, because the scalar is equal to its transpose. So A transpose B is A transpose B transpose. And what is this? It's B transpose times the transpose of A transpose. Where does this come from, this equality? It comes from here. Recall, AB transpose is the same as B transpose A transpose in general. Now, something just to get a little bit warmed up is also good to practice is to look what is A transpose B squared. So it's A transpose B. Well, oh, we are here, sorry. So A transpose B transpose is B transpose times the transpose of A transpose. What is the transpose of A transpose? It's A. So A transpose B is the same as B transpose A. Now if we want to look at the square of this, so it's A transpose B times A transpose B, but A transpose B is the same as B transpose A, right? So then we can write this as A transpose B, B transpose A. And BB transpose is what? Is an outer product, so it becomes a matrix. Another useful identity is this. X minus y transpose X minus y. What is this? Recall that we were here, right? Recall that the length of A is the square root of A transpose A. So whenever you see a vector transpose itself, you should think about length. Okay? Now here we have X minus Y transpose X minus Y. What is that? Now that's the square of the length of the difference of these two vectors. And this gives us X transpose X minus X transpose Y minus Y transpose X. Recall, Y transpose X is the same as Y transpose X is the same as X transpose Y. That gives us two X transpose Y's. And then we have negative Y transpose negative Y. So it's Y transpose Y. So the length of the difference, the square of the length of the difference of X and Y is the square of the length of X plus the square of the length of Y minus 2 times the inner product of X and Y. There is a geometric interpretation that we will discuss later. Okay, so rank, another important concept. What is rank? Rank is the number of linearly independent rows or columns of A. So in order to talk about rank, we need to define the notion of linear independence and dependence. Okay, so what does it mean for a set of vectors to be linearly dependent? Okay, that's the next thing I want to talk. A set of vectors a1 to an is said to be linearly dependent if constant c1 to cn not all 0 can be found such that this is 0. What does that mean? This means that these vectors a1, a2 to an can be added, subtracted, their length can be increased, decreased, and they can be combined in such a way that you get the 0 vector. In other words, and these constants should be non-zero, obviously, because if these constants are 0, then this applies to anything, because 0 times anything is 0, okay? So they have to be non-zero. And when they are non-zero, essentially it means that you can represent any of these vectors as a linear combination of the other ones. So there is some redundancy going on if we want to think about it from a linear algebra point of view. So we have these vectors which are pointing in these different directions. And even though they are pointing in these different directions, it is always possible to represent one of them as a sum of the other one. So sum means sum or subtraction, but it's a linear combination. So when there is linear dependency, then there is redundancy. Okay. Now, if we cannot find such constants, if we cannot find them, if such constants don't exist, if there's no way to combine these vectors so that you get a 0, then they are linearly independent. So if no constant c1 to cn can be found satisfying that, the set of vectors is said to be linearly independent. So the rank of a matrix is the number of linearly independent rows and columns. Okay. And it turns out, I mean, this is beyond the scope of what we're talking, but it turns out that the number of linearly independent rows is always the same as the number of linearly independent columns. Okay. So don't worry, I will make all of these concepts more tangible using examples in R. Okay, I will go over all of them. That will be the next thing. But for now, I just want to go over everything, and then we can move to the practical aspects using R. Okay. Now, the number of linearly independent rows or columns of A. Okay. So if A is n by P matrix, then the rank of A is always less than the minimum of n and P. And if A is full rank, that meaning that all the rows or all the columns are linearly independent, then the rank is equal to the minimum of n and P. So if A is n times P, the maximum possible rank of A is the smaller of n and P, in which case A is said to be a full rank. Okay, so here's an example. A is 2 by 3, right? And what is the rank of A? Well, the maximum rank A can have is 2, right? But that's the maximum. It has 2 rows, 3 columns. The minimum of 2 and 3 is 2. But is it a full rank? Well, just look at this. This vector 1, negative 2, and 3, we have, this is one row vector. And then we have 5, 2, 4. Okay, so we have these two vectors. And there is no way to represent any of them based on the other one. I cannot multiply 5, 2, 4 by something and get this one. There is no way to multiply 5, 2, 4 with something and then 1, negative 2, and 3 and add them and get 0. Why? Because neither row is a multiple of the other one. So even though A is full rank with rank 2, the columns are linearly dependent. We have these 3 columns. When we say the rank is 2, that means that yes, we have 3 columns, but these 3 columns are not linearly independent. They cannot be, because the rank is 2. And why is that the case? Because there exist constants C1, C2, and C3, such that if we multiply it by 1, 5, then multiply it by negative 2 and 2, and 3 and 4, we get 0. Well, finding those might not be an obvious task, but though the computer, it's an easy task for the computer if the dimensions are small, but it's possible. And essentially, what does this mean? If we want to write this in a matrix vector format, how could we do that? How could we write that in a matrix vector format? So we have this matrix A, right? And then we have these three constants, and this is the same as this, because C will be multiplied by this column, C1, C2 will be multiplied by this column, C3 will be multiplied by this column, and then you add them up, and then you get 0, 0. And it turns out that if C1 is 14, you put 14 here, C2 as negative 11, and C3 as negative 12, you add them up, you get 0, 0. So you see, there are these constant 14, negative 11, negative 12. They are non-zero, and we can just show that these and then we put them here, and when we get 0, so that means that these 3 vectors are linearly dependent. Okay. So if A is square, if we have a matrix A that is square and full rank, then it is said A to be non-singular, and A has a unique inverse. What does it mean to have an inverse? We denote it by A to the power of -1. And the point of an inverse is that you can multiply it on either side. So this matrix A exists, and we can multiply it on either side, and you get the identity matrix. And what is the identity matrix? The identity matrix is a matrix which only has ones on the diagonal and zeros off diagonal. So here we have a 2 by 2 identity matrix. Here's an example. A is a 2 by 2 matrix. A inverse is given here. So for 2 by 2 matrices, computing the inverse is trivial. You probably have seen the formula. I will give it to you later. But in general, calculating the inverse of a matrix is a computationally challenging task when the matrix is big. And essentially, all statistics, I can say, I mean, I don't want to say all, but most statistical learning methods, at the heart of them, they are trying to find the inverse of a square matrix. And that is a computationally challenging task when A is large. So a lot of research revolves around avoid dealing with matrix inverses because it's computationally expensive. But more of that later. But for now, you can see you have this matrix A, this is the inverse, and then you multiply them and you get 1 on 1. So, and it's a full rank, right? Because there is no number that you can multiply by 3 and 4 and get 2 and 6. So these two rows are independent. And A is square, it's full rank, therefore we call it non-singular, and therefore it has a unique inverse. And you can, here we multiplied this inverse from the left side. Now we can also try to multiply it from the right side, and you get the same 1 and 1, the identity matrix. Okay. So here a couple of identities. AB inverse is B inverse A inverse. It operates like the transpose. A transpose inverse is A inverse transpose. And if A is square and less than full rank, then A inverse does not exist, and we call A to be singular. Now, determinant is something that we don't deal a lot with. Actually, we don't deal at all. So I will just I will skip it now, and I will get to it when if we need it, I will get to it. Okay. Well, the diagonal elements of a P by P matrix are obviously A11, A22, APP. Trace is another operation that we may deal with. Is the sum of the diagonal elements. It's typically denoted by trace A. The trace A plus B is trace A plus trace B. Trace AB is the same as trace BA. So trace and determinant for now, just I don't want you guys to get hung up on those two concepts. But the rest I want you to understand fully. Okay. So eigenvalues are important. For every square matrix, um, if you can find a vector x such that ax is lambda x, okay, what does it look like? What does it mean? Remember when we talked about ax, a matrix is a transformation, A is a square matrix, so it's transforming this vector, and if this vector happens to be a vector such that the transformation of A is just a scaling, rescaling of x. Okay, so you have ax, and then you get lambda x. So the transformation of x is not exactly x, but still pointing in the same direction because lambda is a scalar. In that case, we say lambda is an eigenvalue and x is an eigenvector corresponding to lambda. Okay. So again, eigenvalues is also like trace and determinant. I will briefly touch them, and when we need them, I will get deeper into them. Okay. It turns out that the trace of A is the sum of the eigenvalues, and the determinant, which I haven't defined yet, is the multiplication of the eigenvalues. Okay. We say A is positive definite if all the eigenvalues are positive. We say A is positive semi-definite if are positive or zero. And it happens that the rank of A equals the number of positive eigenvalues. And let's just hold on here. I want to, before moving forward, I want to do some other uh, examples, but we will get back to the spectral decomposition, okay, at some later point. Okay, so that's it for, I think I covered a lot of um, basic matrix algebra that I hope has been useful for you. Some of you may already have known a lot of it. Some of you may have known it, forgotten it, but this is just to make sure we are all on the same page. Okay? Thank you.